for this box. What should I do? First, I'm going to do, what's my row total? 70 times my column total. 54 divided by my table total of 150. And can somebody help me out with what that is? 25.2. And guys, what would happen? What do we get if we add the expected for the total column together? 54. Because it's saying how many of the 54 would we expect to be. So the row totals should always, the total of the expected values should always match the row totals or the column totals, depending. All right. And so let's see, this one went up by 1, so this would be down by 1, up by 1.2, down by. But don't worry, you're never going to calculate these by hand anyway. Now, let's look at those real quick. As we look at these, you guys, are these different do we see major differences between what actually happened versus what we expected to happen? Are there differences?
Yes.
Would you describe them as large differences, small differences? Okay, so could these have occurred by chance? Maybe. But they are pretty small. And I'm going to say it this way, the expecteds aren't that far from the observed. All right. Now, and again, reminder, this is on your formula sheet. Chi-squared is equal to the sum of the observed minus the expected squared over the expected. Okay? So, do we have observed and expected for each cell? Yeah. So, I could do 23 minus 24, the quantity squared over 24, plus 22 minus 21, the quantity squared over 21, plus 31 minus 28 point. And I'm just going to do a dot, 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 all the way up through 25 minus 23.8 squared over 23.8. So here's what I need you guys to see here. Does there exist a number that can sum up the weirdness of each cell? How far each one is away from what we expected? We can come up with a chi-squared. All right. So, you guys, our conditions for any of the chi-square tests that deal with two-way tables are random check, same as always. Does anybody want to guess what the large sample size condition will be? our expected counts are greater than or equal to 5. Independent is going to be the same as we've always done. Okay, something slightly different. Our degrees of freedom on a two-way table is not just the categories minus 1. You take your number of rows minus 1, so we had 2 rows minus 1, times your number of columns minus 1. We had 3 types minus 1. So you guys, what should our degrees of freedom be in this case? 2. Everybody good? All right, remember when we said up here, the expecteds aren't that far from what actually happened? Like, if I said, does this look like meaningful differences? And we were all like, eh. It makes sense to me. Yes. All right. Now, we have 2 different names for the procedure we're going to do, a chi-square test for homogeneity or a chi-square test for independence. Both of them are done the exact same way. The calculations are identical. Okay, they just have 2 different names. I'd like to say there's a good reason for the 2 different names, but I don't believe that there is. But on the flip side, you have to know it. Okay, so also sometimes we call that chi-square test for independence a chi-square test for association. If two events are independent, they're not associated. So like they go back. Associated equals not independent. Independent equals not associated. So sometimes we call them both things. All right. And so the big difference is looking at how that data is gathered. If your data is representing multiple populations or multiple treatment groups, it is a chi-square test for homogeneity. If your data represents one population and it's looking for related events within one population, it's a chi-square test for independence. A really good rule of thumb to follow, it's not perfect, but it's a good rule of thumb, is that if your data comes from an experiment, it's homogeneity, and if your data comes from an observational study, you should use the chi-square test for independence. All right. So we're going to go through the formality of this and something, we'll start with the very, very basics. Hey guys, this is the exact same table, so we're still talking about the same data set. Is this a chi-square test for independence or a chi-square test for homogeneity? And because? You guys don't need to stress about this that much. All right. So I'm going to state my procedure. My null hypothesis is going to be there is no difference in completion rates for the different types of music. And if that's my null, my alternative is going to be that there is a difference. Everybody good? All right. Before we check our conditions, this doesn't make sense, but it will when I'm done, okay? I'm actually going to show you guys the shortcut in the calculator first, okay? So, So if I go to stat and I arrow over to tests and I start playing around to find that shortcut, as you guys kind of noticed the other last week, we had two different chi-square tests. One says GOF and one just says chi-square test. So the chi-square test is the one that we would do for two-way tables, and then let's just look at what it's asking us for in order to do this. And as we look, there's two, it asks for the observed and the expected, but it doesn't have them in lists anymore. And the reason it doesn't have it in lists is that this 23 doesn't just go with the 45, it goes with the 80, right? Like there's a row total and the table total, all that kind of stuff, okay? So the arrangement of what goes where is important, okay? So what we're going to do is use a mathematical concept called a matrix. I know some of you have been exposed to matrices and some haven't. Either way, if we stare at our calculator long enough, can we see anything that might help us with a matrix?
Matrix. Second.
You guys with me? Okay, so go ahead and choose. So we can't do this yet because we got to put the data in. All right, go ahead and choose second matrix and bring up matrix A. Oh, I screwed up. You're going to go to matrix, and you have to go over to edit, and then you can edit matrix A and put in the raw data. So you might have to tell it what size matrix you want. It's number of rows by number of columns, but you can go in and edit that whenever you want. So just make it match what you have. Does that make sense? Now, as we do this, guys, your calculator only needs the actual raw data. It doesn't, so you're going to give it the matrix of the observed counts. You're not going to give it any of the totals. Your calculator is smart enough to calculate those totals, and it doesn't know whether or not something's a total or not. So you never, ever include the totals. Just the raw data. And then when I go to stat and go back to tests, and choose that chi-square test, it looks like I'm supposed to put the expected counts in matrix B, but that's not what your calculator is saying here. You just can't see what it's saying. It's saying, hey, where did you put your observed data? That's, you put it in matrix A, and this line says, where should I put your expected counts? So your calculator will fill in matrix B with your expected counts when we're done. Yeah.
If we have matrix B like already filled for
it'll override it.
Okay.
So we go down, we hit calculate.
Okay.
So I'm going to do a couple of things here. I'm going to write that chi-squared is equal to 0.562. My p-value is 0.755. And notice it told me those 2 degrees of freedom. So it calculates your degrees of freedom for you as well.
Which one did you press again? Well, like, I just can't find it.
Okay, stat, test,
Oh, and then do that. Okay.
and then you're choosing chi-square test. Is everybody good? Now, like I said, I go to matrix, and you'll notice that at matrix B, you now have something that it tells you have a 2x3 matrix. And then when I hit enter, or if I hit enter on matrix B, it's going to show me an ad. Do those numbers look familiar? Are you guys with me? It gives you all your counts. It gives you the expected counts for you. So this test, you're actually going to run the calculations before you check your conditions. All right. So, typical rule of thumb, there's 2 ways you could do this. You could put your expected counts in parentheses next to the observed counts. That is a commonplace statistical thing. People will know what you mean when you do that. The other thing you could do, let's go ahead and do this real quick. Okay, so, hey guys, let's check that random condition. How was that met?
Random assignment.
Treatments were randomly assigned. Large sample size.
Expected values were greater than 5.
So if you didn't write the expected counts there, you could actually copy the expected matrix down here. It wouldn't be a big deal. You don't need to write them down twice. You can either put them in the table, or if you just want to write them separately down there, that's fine too. It doesn't matter. But you definitely don't need to write them twice. I just want to show you some standard ways that people do it. What about independence?
Individual responses to.
Individual completion of the assignment. Individuals' completion of the assignments are independent. All right, is anybody shocked at our chi-squared value or our p-value? That's a pretty high p-value, right? Is that surprising to you guys? Well, we have such a high p-value because those differences between each expected or actual minus expected, they're not very far apart. So that makes sense to me that we wouldn't see a huge value for chi-squared. All right, so all that's left is to do our conclusion. We're going to say since 0.755 is greater than 0.05, what are we going to do? Fail to reject the null hypothesis. So, therefore, we cannot conclude there is a difference in completion rates for the types of music.